Well, my dear participants, today I am going to talk about histogram, frequency curve, polygon, ogive for a data. So these are the part of the graphics. Most of the material in this lecture I am going to cover from a book, and that is a great book on that is a first course in statistical programming with statistical programming and graphics with R by Brown and Murdoch, and it is Cambridge University Press. So first we will create a data on weight. So these are the some weights which we have created, and then we can dump this data, dump weight, and the length of the data is, there are 30 observations. Create a histogram. So what we are doing here is that we are creating histogram, but we are assigning this object to H1. Now H1 has many information. Say for example, if you print H1, it has many things, that is counts, density, mates, X name, equidistant true, etc. Now suppose we want breaks. So H1 breaks, these are the breaks 50, 51, 55, 60, 65, 70, 75, 80 and 85. So these are the breaks of the histogram. Now we are going to talk about frequency polygon on histogram itself. So here lines we are using. Line is a low level graphic function, and actually the high level graphic parallel is plot. So plot creates always a new plot, but here histogram always creates a histogram. So here these are the high level function, but low level function is to add on the existing plot. So here lines H1 midts on the x axis, and H1 counts on the y axis, and type is equal to O. So we will run and we will get the result. See, we have to run the whole chunk. See, then after that I am going to talk about plot H mids, cum sum. So this is for ogive. We want a new plot, and that plot is plot H1 mids, and on x axis cum sum, cumulative sum of counts, and that is ogive, type is equal to A. And then we can have about stem and leaf also, but I am not going to talk about. Stem and leaf also we can talk, yes. So here we will run this result. And we are getting the result. See, these are the outputs. This is the histogram, and this is the histogram. And before that, yes, this is the histogram, and these are the points of ogive. So these are the midpoints are added. So this is due to the command of lines, and then we want a plot of ogive. So for that, this is the command, and this is the result for ogive, and then we can get the pie chart. So now I am going to talk about base graphics with R, and here I am going to talk about the concepts, etc. There are two type of graphic functions. One is high level graphic function which always create a new plot. Examples are plot, haste, bar plot, dot chart, pie, curve, etc. Number 2 is the low level graphic functions. They add on existing plot, for example, lines, points, m text, lines add lines, like we just use these lines. Then points, if you have a scatter plot and we want to add some other points, so the function is points, add on existing plots. M text, it is to write something in the margin as a text. Then main title of the figure and then subtitle of the figure. So all these are examples of low level graphic function. Now I am going to explain bar chart. Bar chart and dot charts. See, the data VA deaths, a data set in R contains, actually this data set has been discussed by Brown and Mudrock in their great book, and that is a first course in statistical programming with R, statistical programming and graphics with R. So this data set is there. A data set in R contains death rates, number of deaths per thousand population per year in various subpopulations within state of Virginia in 1940. This may be plotted as bar chart. So here the function is bar plot. First thing I would like to show you the data. So this is the data. This is the age group. This is the age group between 50 to 54, rural male, rural female, urban male, urban female. Similarly, 55 to 59, 60 to 64, 65 to 69 and 70 to 74, and these are the classification. Now we want to represent this data in the form of a bar chart, so that here this is the data argument, this is the data set and data matrix, and here this is the beside is equal to true. Beside is equal to true is required because we want bars besides, and legend is equal to true, we want legend also, and y lim stands for y limit. Actually it is between 0 to 90, and then y lab, labeling y on y axis we want the label deaths per thousand, and the main title is death rates in Virginia. So when we will run this command, we will get the result, and result is this one. This is the data death rates in Virginia. So this is the y lab and x lab is already generated, and this is the legend. 50 to 54 is the darkest part, and then 65 to 59, 55 to 59, and then here it is 70 to 74. So almost same trend is in all rural male, rural female, urban male, urban female. So it is like that. Now same data we want to represent through a dot chart, and the function is dot chart. See, position of the dot of corresponding number. Dot chart VA deaths, x lim is equal to, here it is on axis we are putting the limit because the age is between 50 to 74. So here we are keeping x lim 0 to 75, x lab on label x, deaths per thousand, main title is death rates in Virginia. And if you run this command, we are getting this result. This is the dot chart. This is the dot chart. And here rural male, rural female, urban male, urban female, and inside that every group is being represented. Death, death per thousand, this is the title of the figure, death Virginica. And if you want these points, the value between 55 to between 75 to 74, if we want these dots, say filled circles, then we have to give additional character, that is PCH is equal to, say, if you want 16. So you can run this graph. See, now this is the filled character. It is more visible. So we can make these changes. Suppose you want some other title here. So we can write here main is equal to, say if you want to change this, change death rate in Virginica. So now if you want to run this, you just run this command and getting the result. See, death rate in Virginica. So these changes you can make, and plotting character is this. Suppose I change the plotting character. Say for example, if I am writing 17 plotting character, see what comes. See, it is like this. If we write 20, it will be like this. It will be like this, small filled circles. So this way you can make the changes in the pie chart. Pie chart is not recommended by the statisticians, but for the sake of completion, I am going to talk about pie chart. Pie chart displays a vector of numbers by breaking up a circular disc into pieces whose angle and hence area is proportional to the each number. For example, the later grades assigned to each class might arise in the proportions shown in the following figures. See, group sizes, and then labels, we are labeling them, and A, B, C, D. Say for example, 18 is labeled A, 30 is labeled B, 32 is labeled C, like this. So pi, the function is pi. This is the data object, group sizes, and labels. Labels we have already defined, and color is equal to, see, we are giving the colors to these labels. A is gray 40, B is white, say C is gray, D is black, and F is gray 90. So we can plot this and we can see A, B, C, D and F. So this way we can plot the. Then I am going to talk about histogram. The function is hist. See, simulate 5000 observations from normal 0, 1. Make a histogram for the simulated data. Say for example, x is equal to R norm. R norm is the function to generate random observations from normal distribution. N is equal to 5000, mean is equal to 0, SD is equal to 1. Say, if we simulate 5000 observations from normal 0, 1, what should be the mean? Mean should be around 0 because mean is 0. So see, mean we are getting minus 0.013, around 0. And SD should be 1. So it is around 1.99. And if we are making a histogram of this simulated object, hist x prob is equal to true. So this will generate the histogram, and then we are going to add a curve d norm x mean is equal to 0, sd is equal to 1, add is equal to true, lwd is equal to 2. So when we run the whole chunk, we will get this result. See, this is the result. This is the result. This is the histogram which is made on the simulated data, whereas this is the exact curve of normal 0, 1. Both are matching. Actually, this is the very common technique that if you do simulation and you want to compare your results, so this is the best way of, suppose from normal distribution we are simulating observations and we are making histogram on simulated data, and then we are adding exact curve plotted by the function is curve. If both are matching, that means your simulation is correct. So here they are matching, and that is the kind of verification of our simulated results. Now, instead of normal distribution, suppose we want to simulate data and an example with exponential distribution with rate is equal to 0.05. Actually, exponential distribution is very popular among life scientists, and say for example, if you want to study about lifetime of these bulbs, so it will be right skewed. Similarly, lifetime of these fans, lifetime of cancerous patients. So all these characters follow right skewed distribution. An exponential distribution has been a candidate for the long time. So here I am REXP. Instead of R norm, I am using REXP because exponential distribution and 1000 observations are being simulated. Rate is equal to point. This is the parameter. Rate is equal to 0.06. So when we run this, its mean should be 16.22. It is nothing but 1 divided by 0.06. It is 16 point. And then we can make a histogram and we can verify that histogram with the exact curve of DEXP, not D norm, here DEXP with rate is equal to 0.06, and add is equal to true, because if we don't write add is equal to true, it will be a high level graphic function. Say for example, if we have control 2 curve, say DEXP x, and then rate is equal to 1, and we are running from is equal to 0, 2 is equal to 6, and rate is of course default rate is equal to 1. So if we run, it will generate a new plot. It will generate a new plot, and that is this one. This is the new plot. But we want this plot to be added on the histogram. So that's why when we run this generates the histogram, and curve DEXP x rate is equal to 0.06, add is equal to true. So it will add on the histogram generated here. So when we run this, we are getting the results. So we are getting the results. This is the histogram. So this histogram was made on the simulated data from exponential distribution, and this curve is exact curve. So say for example, if we want to change the label X lab, here X lab, say for example, instead of XE, suppose we want to write X on X axis, X lab is equal to, in double quotes we have to write, say for example, say it is time. Then if we run with these changes, see here on X axis time has come. Similarly, instead of histogram of XE, suppose we want some other title. So what we have to do? Main is equal to, this is the main title, histogram of exponential distribution we want to write this thing on the main title, and if we make these changes and generate this, see histogram of exponential distribution has come. Similarly, suppose here instead of capital density, suppose we want to write small letter with beginning with small letter density. So here we have to write Y lab. All these changes are to be made in the hist is equal to density. So now with these changes, if we run, see here small density has come. So these changes you can make in the graph. Now I am going to talk about another distribution, and that is Weibull distribution. Weibull is nothing but a generalization of the exponential distribution. So simulate 1000 random observations from Weibull with shape is equal to 1.2 and scale is equal to 16. So here xw is the variable R Weibull, R norm, REXP, then R Weibull, and n is equal to 1000 observations are being simulated. Shape parameter is having the value 1.5 and scale is 80. So we can generate these observations xw. Control 2. If you print xw, these are the 1000 observations simulated from Weibull distribution with shape is equal to 1.5 and scale is equal to 80. Now with this data we get nothing out of this, but if we make a histogram of this data, the things will be clear. So here hist xw prob is equal to true and y lim is equal to 0, lower limit is 0, upper limit is 0.01, and then we are adding a curve on histogram, that is d Weibull instead of d norm or DEXP. Now we have to write d Weibull. X, for always with curve we always put x here. Shape is equal to 1.5, scale is equal to 80, and add is equal to true. So I have already explained these commands. If you run, you will get this curve. So this is a nice curve, and both this histogram has been simulated, has been made on the basis of simulated data, whereas curve is exact curve. See, there is some discrepancy here. If we increase the number of observations, say for example, instead of 1000, say we have 10,000 observations simulated, and see what changes you will get. See, it is better approximation. It is better. So this way you can add, you can make changes. Here suppose we want to add one more curve on this with the shape 1.45. So the function is curve divisible x shape is equal to 1.45 and scale is equal to 80. Scale is same. Scale is same. And then we are going to write here we have to close. Yes, scale. And then after that you put a comma because these are the parameters of the distribution. You put a comma and add is equal to true. To add the graph, add is equal to true. Then we have to give additional argument that is about line type LTY. Line type is 1, that is the solid line in the first curve. In the second curve, we want line type 2. So, divisible, oh, there is a mistake in this graph, divisible, here we have to put a comma. Now it is all right. And suppose we want to generate the graph. See, there are two. Here we have two lines, one with shape, the solid line with shape 1.5 and the dashed line with shape 1.45. So unless and until we put a legend here, the things will not be clear. So better we should put a legend, and the function is legend. Legend, and here position, the first argument of the legend, so that should be top right, because we want to put here the legend top right, top right, top left, like that, top right. And legend is equal to, say, with shape is equal to 1.5, we should put in double quotes, shape is equal to 1.5, comma, shape is equal to 1.45. And then we have to specify LTY also. LTY is equal to C 1, 2. Why we are writing 1, 2? LTY line 1, that is the solid line, and that stands for shape 1.5. And line 2, line type 2, that is the dashed line, that stands for shape 1.45. So this will put the legend. Now if we generate this graph, oh, there is some problem. Legend, top right, legend is equal to C LTY. There is some problem in legend. Legend is equal to Oh, spelling top right is wrong. Yes, yes. Now, yes, it has generated now. There was mistake in the spelling top right. So now we have got the result, and that is shape is equal to 1.5, and that is the solid line, and shape is equal to 1.45, and that is the dashed line. So this way we can add a legend to any graph. Not only legend, we can say, for example, we can add some other things which we will talk later. Now, details of the histogram. Here we have taken another example. X is equal to R norm 1000, hist prob is equal to true, curve D norm add is equal to true. So here there is nothing new, and it is about the simulation from normal distribution, and then we are adding a normal curve on it. Now in my next video I shall talk about box plot.